So let's take a look at the following problem set. This is on page 13 of the problem set. Notice that we have a balanced chemical equation where we react carbon dioxide with molecular hydrogen to obtain carbon monoxide gas and also water vapor. We are given equilibrium concentrations for all of the reactants and all of the products. And our first question is asking us to determine the equilibrium mixture in terms of the mole fraction of CO. Now, you can assume a certain volume because if one person were to assume one liter, other person were to assume 2 liters, those differences are going to end up dividing out of the problem. So we have concentration of CO is equal to 0.55 moles per liter. I'm going to assume 1 liter just to keep it simple. So remember, mole fraction of CO is equal to moles of CO divided by the total number of moles in the system. So if we look at what we have CO and H2O are 0.55, so that's 1.1 moles. And 1.1 plus 0.5 is 1.6. So essentially we are going to simplify our expression as 0.55 moles over 1.6 moles. Of course, now all you'll need to do is plug this into your calculator in order to get a result. And according to my calculations, that is a mole fraction of 0.343. Notice that that is a dimensionless quantity. That means that all of the molecules, reactants, products at equilibrium of everything that we consider, 34.3% is in the form of carbon monoxide. And this is our solution to part A. So now let's look at part B. Part B asks, using equilibrium concentrations given above, calculate the value of Kc, the equilibrium constant for the reaction. That's also a fairly simple question to answer because we know that Kc is equal to the concentration of reactants over products. Going back and looking at our equation, everything is in a nice one-to-one stoichiometric concentration. That really makes this particular calculation simple, in my opinion. And so we're going to have the concentration of CO times the concentration of H2O divided by the concentration of H2 divided by the concentration of CO2. Now, previously we've seen that H2O does not belong in the equilibrium expression, and the difference here is that this is gaseous H2O and not liquid H2O. So just plugging in our values, we are going to have 0.55 squared divided by 0.3 divided by 0.2. And again, now we have ourselves a situation where we plug and chug. I'm just going to go back and verify I have the right values, and I do. .55 times 0.55 divided by 0.2 divided by 0.3. And I get an equilibrium constant value of 5.04. Which answers part B. In part C, we're asked to find the Kp. And we know that Kp is equal to Kc times RT to the delta N power. Delta N is 0 because we have 2 moles of reactants, 2 moles of products that are gases. Therefore, the Kp is equal to the Kc because this goes out of our expression. And so the Kp, like the Kc, is 5.04. Notice how I box my answers. I think that's a really good idea when you're doing a problem set or taking an exam, just to keep things clear so that I can easily follow your work. All right. Now let's look at part D. Part D asks, when the system is cooled from 2000 Kelvin to a lower temperature, 30% of the CO is converted back to CO2. Calculate the value of Kc at this lower temperature. First of all, I would like to take this opportunity to point out that this is evidence that we have an endothermic reaction. When I increase temperature in endothermic reaction, we are always going to increase the concentration of products that we obtain. And of course, conversely, when we cool the reaction, we're decreasing the concentration of heat, which is a reactant. Le Chatelier's principle will alleviate that stress by producing more reactant. So let's go and set up an ice diagram. So we have CO2 plus H2 We know the equilibrium constant Kc is equal to 5.04, and we are producing CO gas and we are producing H2O gas. We know that at equilibrium we had 0.55 moles, 0.55 molar, because remember I assumed 1 liter of volume. And we had 0.2 molar of H2 and 0.3 of CO2. Zero 0.2 molar of H2 and 0.3 molar of CO2. Those are our initial conditions. Now we know that the change is going to be that 30% of the CO is going to revert back to reactants. So now we don't need an X. Now we have 0.3 times 0.55. 0.3 times 0.55 plus 0.3. That's an ugly point, isn't it? Let me fix that. And plus 0.3 times 0.55. So this corresponds to adding 0.165 to each reactant and subtracting 0.165 from each product. Again, we know the value of K is going to decrease. And of course, at equilibrium, once this equilibrium constant is reestablished, temperatures change. We expect it to decrease. So now we have 0.465, 0.365, 0.385 for each of my products. So now the Kc is 0.385 squared divided by 0.365 divided by 0.465. Now, of course, we have a plug and chug again. And we expect our Kc to decrease, and we are not disappointed. We get 1.30 for our new Kc, which is down less than the 5.04 that we had previously. Finally, let's look at part E. Part E asks, in a different experiment, 0.5 moles of H2 is mixed with 0.5 moles of CO2 in a 3-liter reaction vessel at 2000 Kelvin. Calculate the equilibrium concentration in molarity of CO at this temperature. So 2000 Kelvin corresponded to the temperature of our first reaction, so we know that that Kc is equal to 5.04. And we are going to begin with 0.5 moles of each reactant, and we want to determine how much CO we would have after equilibrium has been established. So again, let's write our ice diagram. CO2 plus H2 yields with a Kc of 5.04, H2O plus CO. Now those are all gases. I'm just, to save time, wanting not to place those initially. We know that we have 0.5 molar CO2, 0.5 molar H2, and of course no established products. The change and at equilibrium. That means x squared divided by 0.5 minus x squared equals 5.04. Now I can take the square root of both sides since both the numerator and denominator are being squared. That's going to give me x over 0.5 minus x is equal to, that should be about 2.23, but let me just double check that. Actually, I'm going to go ahead and do 2.23. And I'm going to let you guys solve the rest of this problem. All you need to do is cross multiply and solve for x. But that shows you how we can completely go through this equilibrium problem in terms of breaking it down, doing each step, and seeing the different permutations that you could be asked to do on a quiz or an exam, or in this case on a problem set. So if you guys have any more questions, please let me know. We won't have any time in class tomorrow to go over any solutions, but I would be happy to use this medium as a way of showing you how the problems can be properly solved.